topic number 5. One question you can write down that what are the criticalities or why Monte Carlo simulation is so critical for the purpose of modeling and analysis, or for the purpose of forecasting purpose or any application. Okay? One application is not better if you try to demonstrate that particular thing using one example. So for example, forecasting. So we are doing modeling and analysis for the forecasting purpose. The forecasting of what? Forecasting of the stocks, you can say, forecasting of the financial implications, or forecasting to the consumption of a particular product which is launched by a company, forecasting of the kind of malfunction can be experienced by a system. Okay? Forecasting of the what you can say, production and demand. Okay? So any one forecasting you consider, try to demonstrate it with the help of an example. First, try to reason, find out the reason that why it is so critical, what are the uniqueness with it, because ultimately it's a mathematical model, right? It is not a purely, you can say, machine learning or based on some heuristic technique. Okay? So some mathematical model works behind it. So then still why it is so critical. Getting my point? Because if you see the simulating model, that is also mathematical model, right? Then what's so unique about the Monte Carlo simulation? That is one reason. Another reason why you are going to use it for the modeling and analysis of forecasting forecast. Forecasting of any one example you can consider, and then you can try to next. Okay? So that is how it makes sense. If possible, try to work out the limitations of Monte Carlo simulation. Okay? So you can consider it as one single question and then you try to answer. What are the limitations of the Monte Carlo simulation if you particularly judge it from the current age required? Understand that point? Because there was some limitations decades back. Then and only this sector allows all these machine learning or heuristic technique to get enter into the domain to further improve the forecasting or the accuracy of the model. Understand? That means the older model has some limitations. Even it is very good, but they might have some limitations. So we should know those limitations. Done? Okay. So now we will briefly conclude this topic. Today we have the last class. So how Monte Carlo simulation works? The primary knowledge. We have seen that why it is important, what are the benefits, okay? What are the limitations. So let's say you take any typical forecasting model. That means forecasting means basically you are trying to predict, right? So if I have a let's say certain characteristic based on some fixed number of parameters, right? And if that characteristic is available, so then can I forecast the behavior of that particular device, behavior of that particular system, behavior of that particular model, right? So say for example, you take the example of any Ph.D or Ph.D based transistors. You know that how the characteristic, it is from the origin to the saturation point, it works out. Then and only we are able to identify that, okay, what are the specific reason of the entire characteristic which that I can use for as a cutoff. Okay, even the device is not in cutoff position, that means power supply is not absolute zero, but I can treat it as a cutoff. What are the reasons that I can use as my linear reason, primarily the active reason or active mode, whatever you call. So most of applications will draw in that areas. And then I also take care that what will happen if I will enter or accidentally entering or purposely entering through the saturation region, right? So even you know that even I want to use a transistor for as a switch, I can. Okay, because I need to do certain changes while we are doing the doping. Because if you particularly want to use transistor as a switch only, so that it should not experience more time in the active region. That should be a cutoff region and that should be a saturation region. You can treat it as on and off. How do we know? Because we know the characteristics. That's why we are able to predict. Understand? So likewise, any forecasting model you take versus Monte Carlo simulation. So what will happen? Now, if you see these forecasting models, those are developed on based on mathematical model technique. First of all, they take the deterministic input. Deterministic means kind of predicted or fixed values. So you know that the sample size, how much there will be sample size. Number two, within the two boundary conditions, what are those variable values? Clear? For example, if you pick a particular piece of a crystal diode or zener diode, and you are going to perform or draw the characteristic of that particular zener diode or crystal diode repeatedly, the same piece. We are not going to replace it with some other pieces. The same pieces I am using. So if at NTP you know that whatever performance it will provide today, nearly same performance it will provide day after tomorrow, even after 5 days, even after 1 year at the standard temperature and pressure. Right? Or I would say that in the controlled temperature and pressure. Right? So that is like a deterministic inputs. Clear? The input is also deterministic, output is also deterministic. So that is the deterministic. Deterministic means you know, isn't it? You generate a high frequency signal to propagate your data to the longer distance. How do we able to capture it in longer distance? Because that carrier is actually deterministic. Maybe a very high frequency signal, but I know where it is actually generated. 1 megahertz, 100 kilohertz, 10 kilohertz or what. Okay? So receiver is already known to it. So that is your deterministic. Okay? So that normal prediction techniques depends on rely on that. Number two, because of it, what will happen? They will capture the uncertainties or variation in input parameter. That means, say for example, there is a change in input, right? So obviously, the characteristic will also little bit deviate, and therefore the output will change. Okay? So what is the one critical thing? Change in input. Because of the change in input, your output has been changed. So there is an uncertainty in the input, but primarily it is in the input side, not in the sample side, not in the characteristic. If input is changing, I know that how the input, my characteristic is supposed to be changed. Understand? Whether it is tending to a positive value or it is tending to negative y-axis or what. Okay? So because of the change in input, I will be able to work out. Okay? Yes. Is it different than the previous characteristic? Answer is yes. Okay? So even if the traditional methods, they count uncertainties, up to the level of change in the reference or change in set point or change in inputs only. Clear? In place of that, you know that in Monte Carlo simulation we have discussed, it consider all possible randomness. Okay? How do we able to do it? Because what happened, it generates the random samples. Okay? That means, for example, at this point of time, if you take a reference of, is it infinite? Answer is no. Okay? Remember that number of samples you are taking, n is always finite, isn't it? You write the fs is equal to 2 times of fm. So that 2 is n. In instrumentation we have been already discussed, but that this 2 will not enough. There will be a variable value 1 to 5, 5 to 10. But in any case, 5 to 10 is also numeric value. 1 to 5 is also numeric value. So for a particular application, you will fix that value or not. Right? Let's say 2 FM is not enough. I will go for 3 FM or 5 times of modulating frequency. But then again, that 5 is also finite. Okay? So in these cases, what Monte Carlo simulation will do, it will try to test between the entire range of sample. If the range of sample in the temperature is the input, range is 10 to 20 times of the maximum modulated frequency. So it will start from 10, end at 20, and then it will try to optimize. Okay, what is the range of samples which gives me help to get the optimal value? Getting my point? Okay. Along with that, you are also changing the input. Getting my point? So that is the reason that why it is mentioned the randomness and availability in the random samples. That's why it is called random samples. Okay, it will try to generate different kind of samples. Okay, it will try at 1 kilowatts also, it will try at 1.5 kilowatts also, it will try at 0.5 kilowatts also, it will try at 2.1 kilowatts also. Okay, and then it will try to, let's say, for example, the distribution function is a normal distribution. For example, so what is the pattern of normal distribution? It will follow Gaussian pattern. That means there is a point where you will get the highest Q factor. Now it can very easily notice, okay, for which particular sample rate I am getting the highest rate. So it will fix that sample. Getting my point? And then it will consider the change in input, and then it is helpful to draw the get the outcome. Next time again it will repeat this task. Okay, so it will repeat this task m number of times. So now what happened with respect to all possible change in inputs? Okay, it will generate some finite numbers of random samples, and out of which it will help you to collect the most optimal sample that can able to mitigate the change in input and thereby able to predict your pattern. Getting my point? So prediction is, remember, not 100% because inputs are changing. So all the time we will keep on doing this task. Clear? So that is how it will be able to help the probabilistic technique. You can use any probabilistic technique you can use. Okay, for that particular finite range to find the randomness in the samples. Clear? That is the two difference between the traditional method, prediction method, and the Monte Carlo simulation which we are going to use. Idea is clear? Okay. What kind of probability distribution? Can be uniform in some case, it can be normal distribution in another case. Okay, so that depends. Okay. There can be a variation in the distribution function. That is not a problem. Okay. Then these are the methods actually what I will discuss with you. Let us take one example. Say for example, let us demonstrate our application of a rolling dice. I know that how many surfaces are dice has? 6. So what are the number of probabilities in the grid? 36. Okay. There are 36 number of possible inputs. Okay. Based on the outcome is depends on all possible 36 possible types of inputs. Understand? So in that particular cases, why 6? Because it has the 6 phases. Okay, so 6 into 6 is actually 36. Now, if application is now my fixed, now let us see how my manual calculation, that means the conventional prediction technique will help, and how the Monte Carlo simulation will be done. Okay, let us first see the Monte Carlo, the manual prediction or the conventional probabilistic technique. Manual calculation means not cutting on the hand, it is primarily a probabilistic, conventional probabilistic technique. Okay. So what will happen? It will try to list out all possible outcomes and their associated probabilities. Okay, fine. What it is doing? It simulates the rolling of the dice by generating random numbers. Okay, so it will try to find out the outcome based on every possible 36 states each time. Okay, because the input is fixed, and let's say you roll the dice and you are getting 1. Okay, now occurrence of 1 depending on because 1 is 1 out of the 6 phases, and then attempt of getting 1 is also 1 out of 6. Okay, so 6 into 6 is actually 36. Out of 36 states, I will get 1 phase. Okay, 1 out of 6 phases. Okay, so it will try to simulate all possible those random numbers. It requires the combinational analysis to determine the probability. What it does, it repeats the simulation thousands of times or maybe millions of times, okay, to get the best possible generated output. Okay. So from previous case, idea is clear. It is trying to change the samples within the boundary conditions, within your definite limit. It's not like that it is getting, you says that, okay, you restrict to 10 kilowatts, so you will go for 100 kilowatts. No. You give a range, okay, your sample deviation is let's say 5 kilowatts to 10 kilowatts. Now it will try n number of finite combinations between 5 to 10. Now it can be treated as a infinite. Okay? So in this case what happened? It repeats all those thousand or million possible opportunities. Okay? Because of what happened, it is approaching the conventional technique, so obviously it will time consume more time. More time consuming means response time is less. Or I can say that my system I can get sometimes satisfactory response. There is no reason behind it. Your conventional probabilistic technique is also good enough to predict your data something around 40% to 70% range. Okay, not more than that. Can you get 80%? Maybe sometimes you can get. Okay, but that around the range of 50 to 60% is very healthy. But if I want to attain the probability something is around 92, 95 or 98% or maybe close to 99%, then what will happen? It will consume much more time. Okay, because then it also has to develop those intelligence. Understand? Okay. And the only variation is the input. So that is why it will take more time. In place of this, what it is doing? It is considering the change in input, also change in sample. So therefore, it will be able to execute all those probabilities and find the best possible combination. Okay. okay, relatively much faster. Okay, so if your response time will be much less. Okay? So that will be the primary difference between these two. Okay. One more important thing: what are the number of steps that can help you to execute the Monte Carlo simulation? So primarily we called it through this author's presentation it has given 3. So sometimes some authors represent it as number 4 also. 4 number of steps. What are those steps? Number 1, set up the predictive model. So in this step 1, what you need to do? Define the dependent variables to be predicted. Of course, that we need to give that what is my outcome, okay, where I want to reach, what is my destination, that is also predefined, have to predefine. Identify the input variables. Okay, that time is an input variable. So identify the input variables for that particular application. Now that application may be related to the input variable, can be itself an input, can be a risk factor, can be a cost factor, okay, can be some other variables, dependent variables, and all this. Okay, so that is going to influence the prediction. Okay, any factor that can influence the prediction. Okay. Estimate the structure of the model that includes all these algorithms used for the analysis models. Okay. So these are the 3 things we need to take care as a step 1. That means the preparation model. Then we are going to specify the dimension or specify the or fix the specifications. Okay, what are my specifications that you need to meet while you are going to perform this analysis and work out the possible outcomes. What are those specifications? How will you be able to do that? So 1, apply one particular probability distribution function to the each independent variable. If there are 3 different variables, so that means you can apply 3 different kind of distribution function, maybe 2 different kind of distribution function. Clear? One is the most simplest one, but that means if there are n number of parameters that may affect the performance of the outcome, now I am free to apply more than one distribution function. Okay, so how do you decide? That you will decide based on the type of input. Okay, so that's why the number of distribution function will be definitely 2 or more than 2. Okay, understand? So it's like you have 2 different kind of weaponry in your hand. Okay, now you can use the suitable weapon depending on your requirement. Okay, so obviously if you have more weapons, your chances of victory is higher, relatively higher. Obviously how to use that is very important. Okay? It will also able to use the historic data and the current inputs. Okay? Historic data fine. So that we preserve, that can be done in the conventional method also as far as the historic data is concerned. Change in input prediction, conventional prediction method is also considered. That is also considered. So no difference. Okay? Then we work out the common distributions that include all possible inputs. Okay? So after the step 2, you will be in position to work out that okay, can I use one particular distribution model now to work out my entire calculations, or I will still need to go for 2 or more than 2 distribution function. Clear? There are applications where you will be able to find or finalize one of the distribution functions. You perform that, let's say, that task using uniform distribution, using exponential distribution, using log normal distribution. Now you came to know that okay, out of the, if I am using 3, that is the amount of time it is being taken, and that is my output. Let's say percentage output is 95%. Clear? And let's say your parameter is the accuracy. Okay? The static parameter is the accuracy. Now I will take the same accuracy because I reached 95%. Now I will be able to try to see that okay, which distribution model has tried to predict what rate. Because I have used 2 or more than 2, so probably one has predicted more than 95%, one has predicted less than 90%, one has predicted close to 90%. Clear? So whichever is performed given the highest proposition. Now, for example, that one is the exponential. Now, next time what I will do, I will use one common distribution function. Again, allow all possible change in input, allow all possible change in sampling distribution within the rate, and then I try to see what is the output. Let's say this time output I am getting 93.9%, which is close to 95. Now you have a choice. Okay, whether you want a very high accuracy or whether you want a simplest possible model. Clear? So that is depending on your application. Once you have done that, run the simulation. Okay, do this desired tasks. Okay, number 4 is the actually report generation and analyzing. Okay, analyzing because you have already pre-calculated output. Try to see that whether you have achieved that particular task or not. If not, then roll out these steps again. Okay, in a cyclic order. Okay? So that is how you can say there are the 4 steps or 3 steps depending on author to author. So this much you can say that you are able to do. Rest you can see. Okay? Any question? Revealing content. If you want, if you have any personal interest, go through it once. You can find some answers. Let's say possible simulation outcomes. Okay, what are the iterative exploration? Some examples in a practical scenario. So those things are given here. That is the reference what we have been used for this lecture series purpose. Yeah. Personally, I have been more input in this particular lecture slide, so that is the reference I have given. Either you refer that or you use this PPT for your purpose. Okay. The last topic, especially Monte Carlo simulation, you may not get much idea from a book, so that's all to try to do. If time would have been permitted, I would have been able to run for a simulation I was thought initially. So that is one. So at least you cover from step 1 to step 12. This much. Okay. That is necessary. That will be more than enough for you also. And the examination. Done? It's a finish. Okay. Good luck to you all. Yeah. And in the month of May, you are going to be graduated. Good luck for your future endeavors. Do well in your life. Okay.